Hi everyone. So last time we just wrapped up the continuous time discrete state space paradigm. In that context we discussed the birth process, the death process, and an entire video actually on the birth-death process. So what I'd like to do now is to sort of switch paradigm and maybe discuss something a little bit simpler, which is the discrete space discrete time paradigm. Now, the one thing to say about the discrete space discrete time paradigm is that this will become sort of the foundation or the backbone for the hidden Markov model, which will be sort of a very important paradigm for data analysis in this class that we will turn to sort of in the second half of the textbook, second half being after chapter 5. So let's briefly introduce it, and I think we mostly have the language that we need for the discrete space discrete time. So this should be sort of a little bit more routine. But again, the idea is that we have multiple different states, or I should say Sn, going to Sn plus 1 and so forth, through which we are passing. And the one thing, or the one difference between the previous paradigm, is that here the Sns do not need to be different from Sn minus 1 or Sn plus 1. So at this point, I don't need to transition. If I were to plot this versus time, and this is my constitutive state, I do not need to transition from state to state at different jump times because there's no concept of a jump time. At this point, I should say, I'm thinking of time as existing in sort of discrete intervals, and maybe I'm here at the first time interval. I stay here at the second time interval. I'm still here at the third time interval. At the fourth time interval, I find myself in the second constitutive state, where I stay for the remainder of the trace. So again, not a fundamental law of nature, but just a feature of this paradigm is that because my time is discretized, sort of being a little bit more consistent with how I carry out measurements and experiments, then I'm allowed to stay in a particular state at various times. So at this point now, it's probably clear that this object here is no longer equal to 0 because I can stay, right? So let's go ahead and talk about the initialization rule and the transition rule. Transition rule will also be easier here because there's no jump times to draw from. So I only am asking at the next time interval, what is my probability of, for example, going from sigma 2, which I'm located here, back down to sigma 1. I'm only asking what's happening here. I'm not asking when it's going to happen, so I don't have to draw that time. So it's much simpler as a paradigm. So let's talk about sort of my initial state that's being drawn from a categorical distribution, and I have m arguments and rho as sort of the array. Same thing as I had before. The probability with the first element of the array being the probability of being found in state sigma 1. The second is the probability of being found in state sigma 2, all the way to sigma m. I have my transition rules, Sn plus 1, conditioned on small sn, also being drawn from a categorical distribution with m arguments, pi n Sn. I'm going to explain what that n means in just a second. But basically, if I were to plot my pi sub n and sort of list all of my constitutive states as follows, then I have here pi n sigma 1 to sigma 1 all the way to pi n sigma 1 to sigma n, pi n sigma m to sigma m, pi n sigma m to sigma 1. What does this n signifies? It's for the more general case, and we won't be considering it very often, where in fact your transition probability matrix depends on the time. So when you have n dependency, we typically talk about a time inhomogeneous transition probability matrix. So this would be a time inhomogeneous transition probability matrix. As most of the time we assume that the probability of transitioning from one state to another doesn't depend on the absolute time, then typically we drop this n index and we simply call it a transition probability matrix. We can call it a homogeneous transition probability matrix, but it's somehow implied if we simply use the word transition probability matrix. So let me go ahead and draw the pi sigma 1 all the way to sigma m, and basically say that I have a homogeneous transition probability matrix, pi sigma 1 to sigma 1, pi sigma 1 to sigma m, pi sigma m to sigma 1, pi sigma m to sigma m. Now, what are some of the properties of this transition probability matrix in discrete time and discrete space, obviously? Well, the rows still need to sum to 1. So rows must still sum to 1. Now, I may stay where I am, or I can go elsewhere, right? So in other words, m pi sigma m prime to m must be equal to 1. So given where I started from, I either stay, this would be the case where m is equal to m prime, or I go elsewhere. But the probability of either staying or going there, or there, or there, all the way to m must be equal to 1. Now again, I'm not putting this down because it's assumed, right? So the boundaries. And that sort of is the discrete paradigm. Now, there's one word that's worth mentioning. And it's the notion of a Markov chain, because that's also going to pop up quite often. So Markov chain, I can think of as the sequence of states from S0 to S1 to S2 and so forth. So the sequence of states here are referred to as a Markov chain. Some people may have heard of random walks, or drunkard's walk, or circular random walks. Those are all examples of sort of discrete space, discrete time, transition probability matrices. So let's talk about the random walk. The random walk is a discrete time, discrete space. Well, I should say the random walk in discrete space and discrete time, because you can have random walks in different paradigms, has a pi which is characterized by the following. It's going to be some probability of staying where you are, multiplied by some probability of moving to the next state, and probably, or 0 of sort of taking 2 jumps. Now, you can also move backwards, that's why it's random, it isn't a birth process where you're only increasing in your constitutive states. You can also go from sigma 2 to sigma 1, or you can choose to stay in sigma 2 to sigma 2, or you can move from sigma 2 to sigma 3. You can choose to move forward, but then all the others are 0. And what about the next one? Well, I can't go from sigma 3 to sigma 1, but I can go from sigma 3 to sigma 2. I can stay exactly where I am, or I can move from sigma 3 to sigma 4, 0 to 0. And then it's kind of clear sort of what the pattern is going to be. The random walk in discrete space and discrete time is going to be a tri-band diagonal matrix. So the random walk, let's just write that down. The random walk in discrete space and time is going to be, and I'm writing the word down in case you hadn't seen it or we haven't seen it before, tri-band diagonal matrix. It's not a diagonal matrix because you have elements above the diagonal and elements above the diagonal and other elements below the diagonal. Notice that again, it's discrete space, discrete time, transition probability matrix, so the rows must still sum to 1, right? Either if I'm starting off in sigma 1, I stay or I move there. And if I'm in 2, I can either move back or move forward or stay. So in some sense, if I want to think about it this way, maybe this is my sigma 1, and I can either stay in sigma 1 or move forward to sigma 2. By the time I'm in sigma 2, I can either move back to sigma 1, stay in sigma 2, or move to sigma 3. And when I'm in sigma 3, again, I can either stay, move back, or move forward, and so on and so forth. If sigma 3 is my last state, then I just simply remove these, and I just write something like this down. There's another sort of variant of random walks, which may be worth mentioning here, and that's the so-called circular random walk. And you can almost guess, based on my drawing, what that circular random walk is going to look like. In this case here, I'm going to have 3, or I'm going to give the example of 3 constitutive states, and they're all interconnected. So I can either go from sigma 1 to sigma 2 to sigma 1, and sigma 2 and sigma 3 are also connected. The difference between sort of a linear random walk, or just a plain random walk, and a circular random walk is that I've connected my states sigma 1 and sigma 3. You're going to say, how does that change my transition probability matrix? Well, now my pi is going to connect my sigma m to sigma 1 and my sigma 1 to sigma m. I'm still going to have tri-band diagonal structure, and the rest will all be 0. Right? So that's sort of an example of a circular random walk. If I had 4 states, then, if I had 4 states, then I would have a sigma 1, sigma 2, sigma 3, sigma 4, and my 1 and 4 would be connected. Maybe I can have 5 states, and then all 5 are connected sort of in a circle. So it's clear here that I need matrix elements that connect sigma 5 to sigma 1, and sigma 1 back to sigma 5 through these here. And by the way, I still have self-transitions because this is in discrete time, so I can also stay where I am. So this kind of completes the paradigm of discrete space, discrete time. We will have a lot to say about this paradigm shortly when we add the assessment rule and sort of build it up towards hidden Markov models like I mentioned in the second half of the text. Maybe I can mention 1 or 2 more things. A lot of these sort of pictures as I'm drawing them here are highly relevant for chemistry, for example, where we think of reaction networks between different sort of reactants. We can model chemical reactions and chemical reaction schemes and so forth using models such as these. So these are highly relevant to chemistry. And it goes without saying that they're also highly relevant to physics. I can think of, for example, particles diffusing on a lattice. Now, Chapter 2 at this point, sort of takes an interlude and then moves on to some more complicated things where we simulate chemical reactions of arbitrary nonlinearity, something called the Gillespie simulation. Throughout these lectures, and whether I do them online or in person, as I work through the textbook, I skip through these starred sections. And whenever a section has a star, there's the title of the section has a little star like this, it implies that the section is advanced and that I will skip it throughout class and online, in part because I want to get through sort of the base of the material as opposed to sort of sinking into a lot of detail in any one given on any one given topic. It's a choice that I've made, but I think it allows me to sort of spend more time with some of the computational simulations and doing some of the computer demonstrations, which I think are also very important. However, if you're so inclined, at this stage, in the lectures, both in person and online, I would be moving to the next non-advanced section, which is going to be continuous space. Now, if you choose to do it, you can look through the advanced section, where I will discuss some chemistry and physics applications of a lot of the ideas that we've presented here. So with that said, thank you.